Alright, so we're going to learn some theorems today. And these theorems are going to help you with the more difficult problems. And it's like trying to break them down. A lot of us, raise your hand and be honest if you've heard the story of David and Goliath. Okay? So Goliath was this huge giant, and David was trying to break him down and just break him down to something more manageable to overcome. Okay? And yes, he did, and yes, you can with these problems. The problems that you're going to see now are long, big problems. And with what you learned today, it's like you're chipping at them and breaking them down into easier problems that you're used to seeing and easily factor. Okay? So you're not going to, you're not trying to attack the problem all at once. What you learned today is so that you can break it down to something a lot smaller of, oh yeah, I know how to factor that. Okay? Here we go. P of x is the polynomial with rational coefficients. This is the big change today. A lot of people don't like that word because it means fractions. Okay? We're going to do a lot of fractions today. Then irrational roots of, equaling 0 that have the form a plus root b that occur in conjugate pairs. So what we just did, I told you, you always have a pair of things. You would have a plus root b or a minus root b, especially with imaginary solutions. So when you have i's in the answer, you will always have both i's. And that's easy to see, pun intended, because you have two i's. Okay? They will always come in pairs. Hopefully you have two i's. If p of x is a polynomial with real coefficients, then the complex roots occur in conjugate pairs. Okay, so complex roots occur in conjugate pairs, as well as the irrational roots occur in conjugate pairs as well, right here. That is, if a plus bi exists, then a minus bi must also exist. If you have a left eye, you must have a right eye. Okay? All right. So a quartic polynomial p of x has rational coefficients. If root 2 and 1 plus 2 are roots, okay, what are the other two roots? Now let me show you real quick, because right now this 1 plus I throws people for a loop. They see this and they think that they were just given that as a factor. But they're not. What they were just given were x-intercepts that look like this. X equals root 2 and 1 plus I. Go with me? If root 2 is a root, and 1 plus I is a root, what will the other ones be? A negative root 2 and a 1 minus I. Okay? These are solutions. These are possible x-intercepts, as long as they're not imaginary. These are zeros of the function, as long as they're not imaginary. How could I write, so it says, what is the quartic polynomial? Like, it's not asking for us to go there, but I'm going to go there right now. What factors created from that root? X minus root 2. I gotta let it marinate for a little bit because this right here is an x-intercept. That would go here to make the factor 0. That's a huge, oh, that's what's happening kind of moment. Yeah.
If you add it to the other side, how could there be a negative?
If you add what to the other side?
The root 2, if you add that to the other side, how could there be like the other term? Like the
Are you talking about the green one that I highlighted?
Yeah, like in the parentheses, when you like put it equal to 0.
Okay, here we go. If I were to put this parentheses equal to 0, and I add this root 2 over, I would get that.
Yeah, so how would you get the negative?
This would be that. It's irrational. Do you agree? This. I think I might have overlooked this a little bit too fast. Irrational occur in pairs. If it was just 2, it didn't have to be positive and negative 2. But irrational when it's underneath the square root. And I can't take the square root of something that's irrational. Guys, what's the square root? Just real quick. I think I might have over-glanced that too much. Can I take the square root of these things?
Yes.
What are they? 2, 4, and 9. Those are clean whole integers that I can take the square root. Those necessarily won't come in pairs. You with me? Those are not irrational. Can someone give me an example of an irrational? Like the square root of what? 3. What's the square root of 3? It's not going to give me a whole integer. What's the square root of 11? We're decimal numbers. And if you're on my number sense teams in UIL, they actually memorize the square root of 1 all the way to the square root of 12 to 3 decimal places. So they know that the square root of 2 is 1 point, so on and so forth. I don't even remember that. But for their competition, they memorize that. So those that have a decimal, those are irrational. Do you understand? Because like the square root of 3 would give me some kind of weird decimal number. Those are irrational. And it's saying that those occur in pairs. Can you tell me what the square root of 2 is? No. As a whole integer. It's not 1. Square root of 4. 2. That's not irrational. But square root of 2 will come in plus or minus root 2. The square root of 11 will come in plus or minus root 11. Do you understand? They have to come in pairs. Okay? Alright, so back what Catherine was saying, when we set it equal to 0 and solve for that root 2, that's this one right here. Okay? So let me highlight it in a different color. Since irrationals occur in pairs, how would I write that as a factor? X plus root 2. Do you see what we're doing? Now, how would I write, if this positive was written like this, and this negative was written like this, how do you think I would write 1 plus I as a factor? X minus that. Do you see it? I'm treating this whole 1 plus I almost like it's a positive. So that when I move it over here, remember we've been doing this with everything else, it has to be the opposite. And some people might actually distribute that and call it x minus 1 minus I. Well, I don't like that. That just doesn't sit well with me. I would prefer to look at it like this and then do the parentheses. You need these parentheses for sure. This one right here. And then I would stress that it's going to be the opposite sign of what it used to be over here. Okay? Then the other one was 1 minus I. So 1 minus I would see like a positive piece, so that when I put it in, it would be x minus that positive piece. You see what I'm doing, guys? So this is one of them. This is the other one.
Would that one be positive instead?
And if I distribute it, it would be x minus 1 plus I. So you could look at them either like this with that, or what I think you should look at it as, it's easier, is x minus one of them, or x minus the other one. This is as difficult as it gets in my opinion. The other things that we do for the rest of the unit, they start to go down. We're like at the climax, pretty much, the top of the hill with all this content in this unit right now. After today, it's a little bit downhill. Still more to learn, but downhill for sure. Okay? Questions? Okay, so let's keep going. Find a polynomial with a degree, with a polynomial of least degree with zeros of that. How many zeros do you see right there? I see 4. Because this one is imaginary. It's complex. So it must come in a conjugate pair. It has to come in a pair that is that. You see that? It feels like a double root, but it's not. They're different. They just come in a conjugate pair. Conjugate means this: the opposite sign of what it looked like originally. Okay? So a conjugate of this would be that. A conjugate of, let's say, that would be this. Those are conjugate pairs. The sign is opposite. Okay? So with this being said, could I do the same to this and say that it's a plus or minus 3? No. Because 3 is not a what? Not an irrational number. If it was root 3, is that irrational? Yes, because it has weird decimals if you try to figure that out. Then this would be in a conjugate pair. You following me now? And then in 4, do I have to do that in a pair? No, because 4 again is a whole number. It's not irrational. Take the square root of 4. 2. Are there any decimals? No. So it's not going to have to come in a pair. Okay? So the only one that I will end up breaking up is I will have the plus or minus I. Here we go. X equals 3, 4, I, negative I. Okay? So this is going to be at least a 4th degree polynomial. So we'll say, what's the factor of 3? X minus 3. What's the factor of 4? X minus 4. How about I? X minus I. How about negative I? X plus I. And then what we're going to do with all this is that we're going to find the polynomial in what form? Standard form. Yeah. So standard form. Here we go. This is all y or f of x, however you want to do it. I'm going to do y because I don't want you to get confused by seeing an x on the left side and think that we have to factor it somehow. Okay? 3 words. What do you see right there? Difference of squares. That means this will end up becoming, if I square the x's, right? And if I square the i's, what does that equal? Negative 1. Let me show you in steps. A difference of squares is when these two are different signs. to give you that. A difference of squares in the way that I'm doing it, this would give you x squared. These i's would give you I squared, which is a -1. So what would these two imaginary imaginary factors FOIL out to be? X squared plus 1. Is there such a thing as sum of squares? No. That's why they came from something imaginary. There's a sum of cubes, but not a sum of squares. Do you see it though? How I'm trying to go back and forth between the way you were taught? And then you still have this to contend with. So I see this, and if I FOIL it out and I distribute, what do I get? You tell me. X squared minus 7x plus 12. Nicely done. And now you can distribute this on both, and then this on both. I don't like to do that. There's 3 different distributions. I'm a little lazy, and I know I'm going to still get the same answer, but for less confusion too, I like to do this, and then distribute the 1. The i's are gone because it became I squared, which is a -1. Remember, we can't forget that I is the square root of -1, and that I squared is just -1. You see how cumulative this stuff is? Alright, so let's do this together and finish this off. No, because I'm subtracting a negative. Because if it was x squared minus 1, that's difference of squares. There are no i's with that. You see what I'm saying? If it was x squared minus 1, this would break up into this. There's no i's involved needed there. It has to be x squared plus 1 to reaffirm that there's no such thing as a sum of squares with real numbers. Alright, so here we go. If I make a mistake, please correct me, and I'll give you 100 points. I'm going to do the black distributions first. So x to the 4th minus 7x cubed plus 12x squared. Now if I do the blue distributions, plus x squared minus 7x plus 12, all this is set equal to y. And from here, I'm just going to group all my pieces together. I see squares, and those are the only things that I need to group together. Okay? So my final standard form equation answer should be y equals x to the 4th minus 7x cubed, positive 12, positive 1 is 13x squared, minus 7x plus 12. Are we good? Now what we're about to learn. We went from the zeros, created the corresponding factors, and we went to the standard form. Now we're going to go backwards. And that's it. That's the pinnacle of this unit. Okay, here we go. We're going to factor from something that looks like x to the 4th minus 7x cubed, this huge 5-term polynomial. We're going to go backwards. Okay, here we go. Oh, wait, maybe we're going to do one more example. Okay, so with the 0 of 3 minus 4. First of all, if this is a 0, is there another 0? Yeah, what is it?
3 plus 4.
Okay, so this is where the confusion lies just a little bit. I heard what you said. Right now, this looks like 3 minus 4i. And it looks like what I showed you, it looks like that.
So it just means
And some of you said, well, then the other one would be the negative of that. Okay, but in our notes, I want to make sure that you understand there's an easier way to interpret this. In our notes, whenever we saw imaginary, all you have to do is the positive and the negative. So when we come over here, we're not going to do it the way I just showed this positive and negative in front of the parentheses. We can just leave them both as x minus x minus. And right here we will put 3 minus 4i. And guess what? 3 plus 4i. You see that? It takes care of both of them, and it treats it as this is going to be minus. That's as difficult as it gets, in my opinion. Right there, that's as difficult, because that was a little confusing, because I would say most of you said to do this. You with me? Because this would give you a negative 3 plus 4i. This would give you a positive 3 minus 4i. And the distribution over here, please be careful of how you do it. Because look, if this is the following, if I said that this was x minus that, and this was x minus that, there's negative mistakes that could happen here. A lot of negative mistakes it's just confusing. But if you treat it as x minus and you put the conjugate pair, you'll be fine. We good? All right. So, this 3 minus 4i and 3 plus 4i, oops, I'll write it right here, are the conjugate pairs that will come from this and that. Okay? And now we're ready to do what? Distribute. Do you see a difference of squares? No, because if you did, one of these would be what? A positive. It would be plus and minus. Are we good? All right, so here we go. Let's distribute, and I'm going to color coordinate this to help you out with organization. Let's distribute this, and we get what? X squared. Let's distribute this, and we get what? We get like a negative x times all of that. Okay? What would we get here? Negative x, same thing. You see what's happening? All I did was distribute these middle pieces right here to get that. And what's the last one going to be? Let me highlight it in green. The last terms that I'm going to multiply together are right here. So that I will get plus, because a negative times a negative, and it'll be that multiplied together.
So would you have to do
More folding, or identify that that's a difference of squares. So let me write it as both. So you could do this and this, or identify, ooh, when I FOIL this out, it's going to be 9, 0, minus this squared. So it'd be 16, it'll be plus 16, because I squared is a negative. So 16 times I squared is a negative 16, and it's like saying 9 minus that negative 16. which again, imaginary roots, it's going to feel like a sum of squares. So this will be 25. See what I'm saying? We're going to simplify this even further, and I'm going to come back to this, because right now I need to show you a couple other things before we leave today that you need to see notes-wise. I will come back to this and finish it up and maybe even re-explain it if you need it, just to make sure that you're good to go on those conjugate pairs of imaginary solutions. But we need to talk about a couple things, because the bell's going to ring in about 10 minutes. Rational root theorem. These are the fractions. What are the roots if you see something like this? This feels like factoring by grouping. I know it's weird, and I know I embarrass myself every year when I do it, but I don't care. That song that goes, started from the bottom, now we go, whatever. Who sings that? Who? Drake? Okay, so start it from the bottom. I'm starting from the bottom. Okay? The last shall be first. You with me? So the leading coefficient is going to go in the denominator, and the last shall be first will go in the numerator. And now you're about to build some fractions. What are factors of 6? 1, 2, 3, and 6. I know. Here we go. What are the factors of 2? 1 and 2. Now, you could have plus or minus on the top, and you could have plus or minus on the bottom, on all of these. And what we're about to do is we are about to, as girls walking into their closet would say, coordinate outfits. Okay? If I go into my closet and I have these jeans, or I have these shirts, and I have these whatever dresses, I could coordinate an outfit. Pair them up. I could create a 1 over 1, or I could create a 1 over 2. Right? I could create a 2 over 1, or I could create a 2 over 2, which is already written as 1.